welcome back, everybody. Last time we introduced propositional and predicate logic as our language with the aim to formulate set theory, and that's precisely what we're going today. And first we have a short chapter on the epsilon relation, and in fact set theory as an axiomatic theory is formulated on a fundamental postulate. Namely, on the postulate that there is a fundamental relation epsilon that there is a fundamental relation. Now, what's a relation? A relation is just a short term for a predicate of two variables. That is a predicate of two variables. It's just quicker to say relation, is that there is a fundamental relation called epsilon. Well, obviously this will be the element symbol that we all expect to make its appearance in set theory, but let's not have any preconceived notions about it. It's simply a relation and it's called epsilon. There will be no definition of what epsilon is, and that's important. There will be no definition in the stricter sense of what epsilon is, apart from it being some predicate of two variables, or for that matter, or of what a set is. Now this is weird, we're going to write down set theory, but I tell you there will be no definition of what the elementary symbol epsilon, the element symbol, actually is, or what a set is. Well, I use the definition in a strict sense, namely saying epsilon is defined like da 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 da, or a set is da 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 da. We're not going to say this. Instead, we're going to write down 9 axioms. Instead, 9 axioms that use or that speak of epsilon and sets. And these 8 axioms will teach us how to use epsilon and what constitutes a set. So it will only be the interplay between the epsilon and what we call sets, which defines what a set is and which defines what the epsilon means. And as I indicated last time, such an approach is necessary if we want to start writing down mathematics from scratch without any prior notions, without any prior terms in terms of which we could define the element relation or a set. Now, which axioms are there? So overview over the axioms. So I memorize them as EE_perp, ICF. So you've got to learn this like a poem. EE_perp, ICF. Well, these EE, they're, let's call them basic existence axioms. So that's their character. And that has to do with the kind of a property of the element relation, and the E stands for existence of an empty set. Of course, we'll specify this. The perp, they are heavily used construction axioms. Construction axioms, which instruct us how to build new sets once we have some given sets. That's, of course, a recurring theme, that if you got a structure, you want to know how to build from elementary building blocks or given structures of this type, new structures. P is the pair set axiom, U is the union set axiom, R is the replacement axiom, powerful thing. P is the power set axiom. Now, I see these are further existence axioms, further existence axioms, but they could also be classified as construction axioms that are a little more advanced and actually are rather newer than the other axioms. And the F is the so-called axiom of foundation, and the character of this is more of a non-existence axiom that says don't use sets of the following kind. Okay, so that excludes something. That's the overview of axioms. And now we're discussing them in turn, and I will discuss them in this order, partly because some of the later axioms rely on the earlier axioms, but then also I want to give some immediate application of each axiom so that we get a feeling for them, and sometimes I push them down the list in this order in order to be able to use some previous application in the more advanced application. Okay, so that's why we have this order, but EE perp ICF, you agree, is a wonderful mnemonic. Okay, so never forget, 9 of them. This is the, these are the initial letters, if you will. So, well, before we go there, let's actually introduce some new relations using the element relation. I'll sometimes call it the element relation. The element relation, we can immediately define, well, further relations. One fashionable one is X not an element Y. So you see, a relation in principle is a symbol that eats two variables. But it is tradition to then put the symbol between the two variables. So if you wish, the right-hand side is defined in terms of the left-hand side, because you save 2 brackets and a comma. And it's the more traditional notation. Just for you to realize this really is a relation between two objects. Once we have, so we define this is defined to be equivalent, not X in Y. And we define a subset relation, written like this, which is defined to be the case if for all A, it is true that A in X implies A in Y. And finally, we define X equal Y. So you see the equality sign, which we would probably normally take without further questioning what it means, is actually defined in terms of the epsilon relation. X equals Y means that X is a subset of Y and Y is a subset of X. And for that subset relation, we use that here. So that's the definition of the equal sign, which therefore ultimately is defined in terms of the epsilon relation. Now, having said that, we come to the axioms, the Zermelo-Fraenkel axioms of set theory. So these are the 9 axioms I talked about, and the first axiom actually declares that the relation between epsilons and sets, so let's call this the axiom on the epsilon relation. What its character is, we know it's a relation, but what its relation to sets. Whenever x element y is a proposition, that means it's either true or false, is a proposition if and only if x and y are both sets. Aha! So you remember that in first order predicate logic, I explained last time, we leave it entirely open what the nature of the variables that enter a predicate, in this case a predicate of 2 variables, what the nature of these variables is. But this first axiom clarifies x element y, that's how we read it, x epsilon y, is a proposition and therefore epsilon a relation, only if it acts on what we are going to call sets. So it's the first thing we know about sets. And that seems so trivial that for a long time people thought this is not much of a, historically, this is not much of a condition. But in fact it is. So let's immediately give a counterexample what is not a set. And this is a very famous counterexample. Counterexample. Assume there is an object u, there is a u, or there is some u, that contains all sets x, or all sets, forget about that, all sets that do not contain as an element themselves. What do I mean by this? Okay, in order to be precise, and we should be precise in order to fix our language before we get more nonchalant with it, to be precise, we assume there exists a u such that for all z in u, for all the elements of u, it is true that sorry, I didn't explain that. So that for all z, we have that z in u if and only if z, I called it, z not in z. Is this right? We have all those z in u that do not contain themselves. Yes. So we assume z is a set, and we assume there is such a u. Now, question. Is u a set? Can this set of all sets that don't contain themselves be a set? Maybe you're worried about this because you have been trained to distinguish very carefully between a set and the elements of a set. And it may disturb you to think of a set being an element of itself or not being an element of itself. But remember, well, and finally, this non-existence axiom will say, don't even look at such stuff, okay? But at the moment, and it's very instructive to consider this. We just said epsilon is a relation, and whenever x and y are sets, x element y is a proposition. Yeah, well, if z is a set, then z element z or z not element z, z is a proposition, right? So at this point, it's perfectly fine to do this. But the question is, this collection of all the sets that don't contain themselves, is this a set again? And the answer is no. But how can we see this? Well, by looking at this axiom, because if U was a set, then one must be able to decide whether U in U is true or false. Why? Well, if U is a set, then U in U must be a proposition. And a proposition is something that's either true or false. Very simple. Well, that's exactly the problem here. But assume that U in U is true. There would be one possibility. And the other one is assume that U in U is false. So one of the two must be the case, because U is defined. Well, if you assume U in U is true, then it must be true. Then U is an element of itself, so it's some particular Z. But then it implies that Z not element Z, so that U not element U. It immediately follows from the definition of U that U is not in U. That's a contradiction. So we assume U is in U. It implies U is not in U. Aha. What does that mean? Well, it means that this assumption cannot be true. Not a problem yet. If that's not true and it's a proposition, then it's probably false. No, it's not probably false. It must be false if U in U is a proposition. So let's investigate that case. Assume U in U is false. If U in U is false, that is equivalent to saying that U is not in U, no doubt. That's the definition of not being an element of something. But if U is not in U, then it must be in U, because U contains all those sets that don't contain themselves. So that's the definition of not an element of. But then it follows by the definition of U that U is an element of U. Oh, that means the assumption that it's false also leads to a contradiction. There's only one conclusion. Conclusion: U is not a set. This is the Russell drama, or you can call it the Russell paradoxon. So this is Russell. Russell and Whitehead wrote two thick books, the Principia Mathematica, on logic as a basic language for mathematics. So Russell, Whitehead, big Cambridge professors, philosophers, logicians, mathematicians, whatnot. And they wrote these two thick volumes, and they thought they built, it's the work of their life, and they built this language, this foundation for mathematics. But it was not this set of axioms. It was what today we polemically call naive set theory, and which is taught usually at school and in undergraduate courses. We use naive set theory. And in naive set theory, you can easily make constructions like this. You would, in school, you would maybe write U is defined as the set with all those elements Z that have the property Z is not an element of Z. This is just the standard notation for this. You condition elements to be in a set, I mean, mind you, we haven't introduced any such notation yet, okay? But that's the idea of what is written here, okay? And so you easily construct things, objects that are not sets. And Russell, after they wrote these two books, and he discovered this contradiction, this antinomy, he actually couldn't sleep well, and he had nightmares about the big Cambridge library, people taking the two volumes and throwing them out of the window and stuff, and it's all his life's work and so on. So it's a drama, and but finally the resolution of this drama and other dramas, other contradictions, inconsistencies of naive set theory were finally resolved in a big struggle by a number of people, and today we honor Sermolo and Fraenkel in particular for coming up with a set of axioms that deal with this in a better way. So the first axiom, fine, but you need 8 others in order to not run into difficulties. But the first axiom already tells you this would be a problem. Any question? So we completed E, the first E. Now we go for the second E. The next axiom is the axiom of the existence, or on the existence, of an empty set. And that's an easy one, very important. There exists a set that contains no elements. What does that mean? Well, we agreed on having a precise language. That means there exists a set, let's call it X, such that for all y, it is true that y is not an element of X. This is the precise formulation of the statement: there exists a set that contains no elements. I will carry on for a while to formulate the axioms in this fashion, in this formal language, so that we see how that works. So in principle, up here, we could have, and maybe we should, also write down the formal version of this axiom. So let me bring this down again. So the formal version would be for all x and for all y, x element y is either true, either or, we defined this exclusive or, it's either true or it is false. If you wish, this is the statement that this is a proposition, it's this tertium non datur, there is no other possibility, it's either true or false. Okay. Well, this is a little bit unnecessary. We know what it means to be a proposition. Now, this is the existence of an empty set. Now, we have an immediate theorem, which is very simple. There is only one empty set. There is only one empty set. And because there's only one, we can give it a name. Call it empty set, a 0 with a slash. Now, what's the proof of that statement? And I'll give 2 proofs. Same idea of both proofs, but the first proof is the standard textbook style proof, which in this case, it doesn't mean that the textbooks omit something or not precise enough. Well, it actually means we use our standard way of thinking about these things, and it goes as follows. Assume x and x prime are both empty sets. How do we prove that there's only one? Well, we have to show if this assumption, that this assumption leads to the fact that x equals x prime. So if two empty sets are always equal, then there's only one. Are both empty sets? Well, if that is true, then I can write down something like y is an element of x. And what do we know about this proposition? If x is an empty set and I write down y in x, it's false for whatever y is, right? Because the empty set has no elements. But if this is false, then I can write an implication arrow, and here I can write whatever I like, and the whole statement will be true. Correct? And I happen to like to write a y element x prime. Well, if I can write whatever I like, I mean any proposition I like. Okay? I do this so the whole thing is true independent of what y is. Is that correct? But if that proposition is true independent of what y is, we learned it's the definition of the all-quanter to then have this whole thing being true if the proposition is true independent of the y. Aha! Yeah, but this just means by definition that x is a subset of x prime. That was our definition of what a subset is. It's still up there. Yeah, conversely, same argument, I can write down y an element of x prime, and this is always false. Why? Well, because x prime is an empty set. For an empty set, y in x prime is always false. If this is always false, I can write an implication arrow and write down another proposition of my choosing. I happen to like y element x. Because if this whole implication, this whole proposition is true independent of y, I know that the all quantification of this is true. But this means, but thus, x prime a subset of x. So in summary, x subset of x prime subset of x, both together hold. So in summary, x equals x prime. Aha! You take two empty sets, they must be the same, meaning there is only one empty set. Very elementary proof. When I say a very elementary proof, didn't we define what a proof is? Does this have the form of what we define what a proof is? No, it doesn't. So we'll give a precise proof, formal version. And we will only do this once. Okay?
Just a question which is bugging me all the time. Does x being a subset of y imply that x is an element of y? You just, right, oh, sorry.
No. There's an element relation, and what a subset is, unfortunately I erased it, what a subset is defined in terms of that, but it's not the same thing.
I didn't say equivalent to, but implied.
Say again, what implies what?
Does x being a subset of y imply that x is an element of
no.
y?
Okay. No. Okay, neither direction. Okay, which is easy to check. Yeah. Find counterexamples for both directions. Okay. No, but I appreciate the question. Okay. So the formal version, how does that work? Well, the formal version, we have to encode our assumptions as axioms. And what's the assumption? Well, the assumption is x and x prime are both empty sets. So we assume we have here for all y y not an element of x. And the second assumption is for all y, y is not an element of x prime. These are two assumptions, namely, we'd say, this means x is an empty set, this means x prime is an empty set. That's right. And now we need to write down a string of further propositions. Well, if you want to be very picky, propositions are not equal to each other, they're equivalent to each other. So if you want to be very picky, we have to write this. Okay, we should be picky maybe. And finally, we want to arrive down here at the statement we want to prove. So at some mth step, m to be determined, we want to have the statement that x equals x prime. And the task is to find these steps in such fashion that for every step of the proof, so these are the axioms of our system, meaning assumptions for the proof, because apart from this, we only want to use we only want to use propositional logic, so therefore these amounts to the assumptions, because propositional logic only would be an empty set of assumptions. Now we have the assumption x and x prime are empty sets. So now we need to find such steps such that we arrive here, and that for every step we can tell which of the deduction steps, T, tautology, A, axiom, or M, modus ponens, which last time I wrote down in the definition of a formal proof, justifies this particular step. So, okay, so how does this start? Well, the first thing, we write down a tautology. And that is, if for all y, y is not an element of x, that implies that for all y, y is an element of x, implies y is not an element of x. Let me see whether this is what, so you see this nonsense, is an element of x prime. That's what I wish. It doesn't matter. I can again write here what I want, so I want this. So, well, why is this true? Well, you see here, this would be true. Well, if for all y in x, this is implied. But if I make it a condition that y is not an element of x, then ex falso quod libet, this thing is true. So if you put the brackets here right, that means the brackets around here, I don't need to write them, brackets around here, this whole thing is just true for any y, x, and x prime. This is simply a tautology. So the reason why I can write down this Q1, it's a tautology. Okay? Right. So now I pull one of the axioms. I take the first axiom, so I write Q2 is the proposition for all y, well, it's a scheme of propositions, y is not in x. Why can I write this down? Well, by deduction rule A, you can pull any of the axioms into this list of steps compared to the definition of proof. And then Q3, we use the modus ponens. That's the third deduction rule, M. What did it say? It said that you take two prior steps of the proof. Well, there's only these two. And you put an and between them. So you take this and this whole thing. And what you then can write down here is something that follows from this, in the sense of you take Q1 and you take Q2, and then you can write down Q3 if the implication that this one and this one gives Q3 is a tautology. That was the definition. And it turns out that if you take this and this, it implying this for all y, y in x implies y in x prime, actually is a tautology. So you can postulate, no, you can put the Q3 of this shape into the list. Okay, So this is certainly something you probably want to have a look at again at home and very carefully check the definition of what a proof, what constitutes a proof, and you will find that this is the deduction rule M that allows you this. Now, this, however, is just a short form, so we can immediately, we recognize that this statement just means X is a subset of X prime. It's exactly our definition. So for our own thinking, so it's just an abbreviation to write that this statement is just X is a subset of X prime. And so you see, this is also something we arrived there, well, almost in one line. Here we used a number of lines. Well, because this is a formal proof, I shouldn't write similarly, but it's totally clear that you now do steps Q4, Q5, and Q6, which are really similar. Okay, let me write them down quickly. You again employ a tautology. You say for all y not an element of X prime implies for all y in X prime implies y in X, because this is a tautology. Q5, you pull the second axiom A2 down here. So you write for all y indeed, y not an element of X prime. And then for Q6, in exactly the same fashion, let me write a bit over here, you can now conclude that Q6 is a valid step of the proof if it has the form for all y in X prime implies y in X, which again, in our thinking, well, or in this short form means X prime is subset X. And then you again can invoke the modus ponens and say, look at two previous steps in the proof. In this case, look at, so I should write down. So this modus ponens used 1 and 2. This modus ponens used 5 and 6. And this modus ponens here used steps 6 and 3. No, it used 4 and 5, I'm sorry. 4 and 5, and this used 3 and 6. And you can check that obviously this and this implying this is a tautology. Hence, you can write this as the 7th and final step of the proof, which says the two empty sets are the same. This is the formal proof, and obviously it is nothing more and nothing less than breaking down the standard textbook style proof in a really pedantic manner, but we're certain now this constitutes a proof. There is really only one, just one empty set. So you see we took the whole thing on two levels. From the kind of standard mathematical language formulation, there exists a set that contains no elements that kind of corresponds to this kind of standard textbook style proof. Or we can be very precise and use our first order predicate calculus, predicate logic, and then mirror this in this very formal version of the proof. This is how, that is the spirit of axiomatic set theory. You're just very precise about what you're going to say, and you've got to be very precise. However, we are not going to follow this very strict formal proof technique any further in this course, because the proofs get longer and longer and longer, and there is actually no book of mathematics that spells out all the proofs for all the theorems it proves in this fashion, because it becomes practically impossible. But it shouldn't be impossible in principle. Okay? So that was what I already was hinting at last time, that in principle you must somebody presenting a proof must be able to break it down to this level, although in practice this is certainly, well, hasn't been done for anything serious, as far as I know. Okay, so where are we? I should note this EE perp ICF. So we got this one and we got that one. There are 7 more to go. So the next is the axiom on pair sets. It's a bit tiring to go through all the 9 axioms, but on the other hand, this is the foundation for all of mathematics. So it's worth it, right? What is it for a number, for a field, like the real numbers, it's Carney, it's also 9 axioms to define a field. Commutative, associative, neutral, inverse for plus, same for the multiplication, and 1 distributive law. So, I mean, certainly to build all of mathematics on these 9 axioms is not too bad. So the axiom on pair sets is the following. Let x and y be sets, then there exists a set that contains as its elements precisely the sets x and y. That's it. And the key word is there exists a set. That means you take one set, you take another set, and you put them together as elements of a new set. And this new thing you constructed this way is a set. And that is what this axiom assures us of. So there is, okay, how do we write this? For all x and for all y, there exists a set, let's call it M, such that its elements are precisely those, such that for all u is an element of M if and only if u is x or u is y. For any sets, there exists a set such that all its elements, or that its elements are precisely those that is either x or y. Would be the exact formulation. The usual notation for this is denote the set M, this set M, by the elementary school thing. The set with the elements x and y is denoted by open a bracket, x, comma, next element, close the bracket, full stop. Okay, but that this construction, I mean, I can write this down all right, and I could put a little flower on the right upper corner as well, right? I can write down what I wish. But what the axiom assures us of is if x is a set and y is a set, then this whole thing counts as a set, is a set. We need to have an axiom that assures us of this. Now, there might be an initial worry, and that is, why didn't I call it the set y and x? Why do I call it the set x and y? I introduce an order here, right? Worry, is xy the same as yx? This thing is defined between sets. Is this the same? The answer is yes. It is. No worries. Why is it? Well, if an A comes from xy, that implies that A comes from yx. And if A comes from yx, that means A comes from xy. How do I know this? Well, by employing the element relation and stuff like this. That means x is a subset, that means the set xy is a subset of the set yx, but also the other way around. So in total, they are the same. So our notation doesn't introduce any prejudice, or what you learn in elementary school is the order doesn't matter. We agree the order doesn't matter. No, we don't agree on it, we prove it. Okay? But that the whole thing is a set is guaranteed by the axiom on pair sets. And by the way, so one more remark. Well, or if you want remark definition, it's really trivial. The pair set axiom also guarantees the existence of sets of one element. If I write this, I take a set X, so the X is a set. I take a set X, then I define this set X as the pair set of X with X. Oh well, if X is a set, then X is a set, then I can use the pair set axiom, and I call this the set of one element. And by a similar argument as here, you can see you have the X in there twice, but because equality is defined by the element relation, the pair set with the elements X and X, there is no more information than that X is in there. Okay, you can think about that too. So what we have from the pair set axiom is we have these one element sets and we have two element sets. That's it. At this stage, there is no justification to write down for sets x, y, z a set with the elements x, y, z. It's not defined, okay? It's not defined. But we have these two. However, the pair set axiom will make its appearance again very soon. So probably the most demanding task at this stage is to get rid of old prejudices about what a set is and what the whole thing means, and to free your mind from that in order to appreciate the systematic definitions that we make. And some of the things you thought you can do with sets will simply not be allowed by the axioms we write down, but therefore we must appreciate how what we already knew is consistent follows from the axioms. It's a little like learning about well, number fields or groups or whatever, and realizing that, say, the commutative law between real numbers is something special. You have to write this down as a law in order to use that a plus b is b plus a. And okay, fine. So it's the pair set axiom. The next thing is in our EE, we have the P. The U is the axiom on union sets. Axiom on union sets. Takes the following form. Let X be a set. Then there exists a set that contains, or whose elements are precisely the elements of the elements. The elements of the elements of X. Okay. So I leave it as a homework for you for all the further axioms that I write down to convert this language description, which should be clear in the standard sense, to convert it into first-order predicate logic statements of this type. Okay? It's a very good exercise in order to make very precise what you mean. So if you think you understand it, what it means, put it in first-order predicate logic language. Okay? Then there exists a set whose elements are precisely elements of the elements of X. Notation. Maybe you expected something different from union. You think, the union, don't you need at least two sets in order to build a union? Well, the set X is already the collection of all the sets that are to be put into the union. So notation, there exists a set, let's call it U, notation, U is usually written as a big cup, and behind it you write the X. But still doesn't quite look like the elementary school thing. So let's write down an example. As an example, let A, B, and C be sets. Okay, we start with sets A, B, C. And then it follows that, what do? I take the set with the element A. What do we know of this? If A is a set, we know this, with the brackets around it, is again a set. How are we guaranteed that this is again a set if A is a set? Which axiom? Pardon me? The pair set axiom, exactly. Take this one. Now, take the set BC, the set with the elements BC. Again, the pair set axiom tells us this is a set because B and C are sets. So this is a set and this is a set. So I can put them together into a set. Is that right? How am I guaranteed that this whole last line is a set? Again, the pair set axiom, step by step. So this is a set. Well, let's call this set X. Let X be a set. All right, we constructed a set X. What is the union of X? Well, the union of X contains all the as its elements precisely. Okay. Let's only use a one-element set here. Okay, the example is a little bit more elementary at this stage. Okay, A, B sets. This is a set. This is a set by union set axiom, pair set axiom. Again, pair set axiom. X is a set. Now, what's the union of X? It's the set that contains precisely the elements of X. The elements of X are the set with the element A and the set with the element B. And it contains the elements of the elements. So it's the set AB. And we already know this is a set. And that is what the union set axiom assures us of. What comes out here is a set, independent of whether we previously know it's a set. Here we knew previously this is a set. But the union set axiom says it's always a set, whatever set X you started with. So the second example would be, we know that if we start with X equals A, B, C, so the example I first wanted to write down, we know this is a set. That we already know is a set. All right. But then it follows that the union of the elements of the union of X is a set. Why? Well, because of the union set axiom. This is a set. And this set deserves a name. If it's a set, it deserves a name. And so I define A, B, C, the three-element set, I define in this fashion from two-element sets. Okay? So how do I know? This is just a symbol. Again, this is just a notation for this thing if X is given like this. But that I know that the object is a set, that I know from here. Okay? I mean, in elementary school you learn this is a set, but how do you know? It's just claimed. Now the axiom tells you this. And of course the second example immediately generalizes to a definition. The definition is this. Let A1, A2, ... to AN. Again, what are these numbers? They're again the Bavarian beer counting numbers, 1 stroke, 2 strokes, 3 strokes. They're meta-mathematical numbering, if you want. I could call them A, B, C, D, and I could do this for all instances. Let A1 to AN be sets and then define recursively the symbol A1 to AN. I put them all in brackets. What on earth is this supposed to mean? It's supposed to mean the union of which set? There must be one set behind this whose elements I take and put into the union. It's the union of A1 to AN minus 1. It's the mathematical subtraction. You take one stroke away with the one element set AN, and you define this for all n greater or equal to 3, because for n equals 1 and n equals 2, this recursion is started by the pair set axiom, but now this defines anything that we would informally call a finite element set with specified elements. You get it this way by a combination of the pair set axiom. You already know from the recursion step before, this is a set and this is a set. Then you use the pair set axiom to write down the set of which you take the union. Now, the big thing about X, assuming that you can collect all the sets that you want to unify in a set, is an assumption, you see, because you remember Russell's paradoxon. There we had a U that contains all the sets that don't contain themselves. This U is not a set. So this U, this Russell U, which is not a set, could never be put here instead of the X in order to make a union of all its elements, right? So it's a big restriction that you can build unions only of, let me informally say, as many sets as still fit into a set. You could take more sets than fit into a set. Like, for example, the set, if you take all the sets that don't contain themselves, you cannot collect them in a set anymore, okay? So you could never take their union. This is the big thing about writing down this. It's much more than saying take only finitely many sets and write down the union. That's quick, yeah. But the idea to, and certainly contains an idea of taking infinitely many sets, roughly speaking, but it doesn't mean taking more sets than fit into a set. That wouldn't work. You see, this is subtle, but also very precise. And now we probably got back all the elementary school ideas at this point. A set is a collection of elements. Well, what is that supposed to mean? But now we know very clearly what a finite, you take elements and you put them into the brackets. But you see, this is just a symbol that this constitutes a set in the sense of set theory is guaranteed by the first 4 axioms we had, by the E, P, and U. Okay, there's the replacement axiom. Let me perp is just nice, but it's actually pupper, because I would like to first write down the axiom of the power set, simply because the replacement axiom takes a little bit more work. So axiom of existence of power sets. No. Let me take the R first. Now I remember why I want that. It's not logically necessary, but it's pedagogically better to first take the axiom of replacement. Sorry? Axiom of replacement. Very innocent sounding name, one of the most powerful axioms, and takes some work. Let R be a so-called, and I'll explain this in a second, a functional relation. So not functional relationship, but functional relation, okay? So we may assume its existence. Let R be a functional relation, and let R be a functional relation, and let M be a set. Then the image, I need to explain these terms in a second, then the image of M, of the set M, under the functional relation R is again a set. So you see, the axiom is a construction axiom. The axiom guarantees you start with a set M, then you construct the image of M under a functional relation, whatever that is. I'll explain in a second. But the result is a set again. The axiom guarantees the result is a set. Now, here, or everywhere, we have the following definitions. A relation R, remember, a relation is a predicate of two variables. Relation R is called functional if for every x there exists precisely, I didn't define this, there exists precisely, but you know what it means, and you could define it precisely, so homework, yeah? How would you define homework? So instead of an examples class this week, a problem class, I give you these various pieces of homework. To define what this means, there exists precisely one y such that R of x and y. That's what you call a function, right? I mean, you start with something, and to every x there is assigned precisely one y. For another x, maybe another y, but not necessarily. Okay? Note that at this stage there is no talk about x having to be a set or y having to be a set. It's just a functional relation, nothing to do with sets. Okay, so that's the first definition. And the second definition is the image of a set M under a functional relation R has as its elements, yeah, or consists, I write consists, and you'll ask in a second, I'll answer in a second, consists of all those y for which there is an x in M such that R x comma y. And if you're careful, your alarm bells should ring, because I put here the word consists, very harmless word, but of course wherever I wrote consists before, I meant consists of all those y, I mean has all those y as elements. The image has all those y as elements, which I reach from some x by rxy, right? But you say, hang on a second, how do you know that all those y are the elements of something, are the elements of a set? Who tells you that all those y's I arrive at constitute a set again? How would I know? How can I write this down? Well, the answer is, I write this down, I make no such assumption, but it's in fact the axiom of replacement that guarantees this. The axiom of replacement says, then the image is a set, is again a set. Okay? So that's the logic here. It is guaranteed by postulate by the axiom of replacement. Now, you very likely haven't seen this before. And that's surprising because I said it's one of the most powerful axioms. How come we haven't come across it? Well, you have come across this axiom, I think even in school, in high school, but it came in a weaker form. And the weaker form is called restricted comprehension, which follows from the axiom of replacement, which I'm going to write down in a second. But the axiom of replacement is slightly stronger, and in order to have all of modern mathematics covered by our set of axioms, we need a slightly stronger axiom of replacement. But in this course, we'll actually never again, I think, we'll never again really need to invoke the axiom of replacement, but only its weaker conclusion, namely the principle. Let's not call it an axiom, let's call it a principle, because it's just a derivation from an axiom, the principle of restricted comprehension. I'm going to write this down now, and you will recognize it. The axiom of replacement implies, but is not implied by, the principle of restricted comprehension. Which is the following. Let P be a predicate of one variable. And let M be a set. Then those elements y in this previously given set M, for which P of y is true, or holds, constitute, then those elements constitute a set. Notation. This set is usually denoted, but its existence is guaranteed by the principle of restricted comprehension, which follows from the axiom of replacement, is usually denoted the set that contains those y in M for which P of y holds. Right? And you saw this before. You do this all the time. You say, select those elements for which a certain condition applies. Standard stuff. But didn't I tell you just a few minutes ago that this is not consistent? I think we had this on the blackboard. So, not to be confused. So the principle of restricted comprehension is not to be confused, with the inconsistent principle of universal comprehension. Which Mr. Russell had his problems with. And this principle of universal comprehension stated that I can say, collect all the y for which P of y applies is a set. Well, sick, right? It's not a set. This is not true, right? So the principle of universal comprehension says you can collect all the y for which a certain property holds. But this is too much. This could be all the y for which y not an element of y. This is the problem. What's the difference? Well, the difference is that up here I need to tell from start a set M from which I select these elements. So intuitively speaking, if M is already a set, which is what is assumed, and then this thing here can't make it bigger. You at most kick out some of the y's that don't make this condition, but the whole thing cannot become bigger and bigger and bigger than M. But because M is already a set, this is not unbounded, this is not unrestricted, it's restricted comprehension. So the restricted in restricted comprehension, the restricted is this bit. It's restricted to come, the elements are restricted to come from an object that previously has been known to be a set. Okay, so this is the principle of restricted comprehension. Well, we need to prove it. Proof. From the axiom of replacement. Well, that proceeds as follows. Case 1. It could be that there exists no single y in M for which P of y is true. It could be that there is no such. Did I define what it means there exists y in M, or only wrote exists a y? So anyway, so the idea is there exists a y in M such that something, this is defined as, there exists a y such that y in M implies the very same something. Now, I mean, first order predicate logic only has this. If I restrict here like this, it's just a short form of saying I condition it on y being in M. Very simple. I don't remember whether I said it. Okay, so case 1 is there is no y such in M such that this would ever be satisfied. In this case, we define, well, I mean, this is just a symbol. I need to define what the symbol means, and the symbol is then defined as the empty set. That's pretty clear. So we don't need the axiom of replacement. It's just our clear statement of what this set we are constructing, how it is. And this, the empty set is a set, so this thing is a set. This is what the principle of restricted comprehension says. But then in case 2, that's obviously the complement of this. There exists a y in M such that P of y, and let's call this y, let's give it a special name, it's a y hat. There is a particular y hat for which it's true. So there's at least one y for which it's true. Take one such y hat. Take it. Okay? And then define, well, if we want to relate to the axiom of replacement, we better construct a functional relation. And we define the functional relation xy, r of xy, as P of x and x equals y or not P of x or P of y. P, hang on. P of, hang on, what did I, which way around do I do this? No, P of x, correct. Or non-P of x, and then x equals, no, and then y equals y hat. Am I happy with this? Yes, I'm happy with this. So you see, I picked a particular y hat which happens to satisfy the condition. Take one of those, a specific one of those. And then define a relation of two variables, x, y. The x and y appear on the right-hand side, so a relation of two variables. There also appears a y hat, but that's a fixed y hat. Okay, we picked this. And the claim is that this relation is functional. R is actually functional. What's the idea of this construction? The idea is we want, after all, we want to take all the x in M for which the condition applies. Well, if the condition applies, then take just this x as the image y. But if the condition doesn't imply, a functional relation requires it maps to something, you every time map all those x's where it doesn't apply, you map them to the one y hat where it applied. That's the idea. You need to stare at this at home for 5 minutes, and then you say, ach so, okay? Fine. So this is functional, this is the case, and then we define the set y in M for which P of y applies. You define it as the image of the set M under the functional relation R. And that's just my notation. I could write out what's written up there. Yeah. Don't worry if you don't see it immediately. You've got to stare at the definition for a while, and then you understand this is absolutely correct. Right. So as I promised, we will rarely invoke the axiom of replacement in full. We'll only invoke this restricted comprehension, and we're very familiar with this, so there's no problem. You just now know where it comes from, and obviously there are a number of conclusions you can make. For instance, you can define the complement. Let U be a subset of M, they're both sets, yeah? Then M without U, what is this? M without U is the collection of all those elements of M for which X does not lie in U. Obviously, that's the complement, and everything is fine. X in M, this is restricted comprehension, so because of restricted comprehension, we can conclude is a set, so therefore this is a set due to principle of restricted comprehension that is ultimately due to axiom of replacement. But you see, this is a little bit more cumbersome to use. This goes more easily. And then again, as a homework, I leave you with definition of the intersection of sets. So let X be a set. Define the intersection of all the X. And I leave it to your imagination of how you do this, and I just tell you, use restricted comprehension. Okay. Homework. So we can do more and more and more. And you see unions, you've got to define them. You've got to postulate the existence that this is a set. The intersections, you conclude it from the axiom of replacement. Okay, I already made the historical note that the principle of universal comprehension is far too powerful, but you can now see, well, you'll see in the next axiom, why people thought that you need this. But are there any questions so far?
Yeah.
Yes?
Where you define the exists y element M in bottom line.
Sorry, where you define what?
In bold.
Yes?
where you say exists in the bottom line.
Yeah.
Can I not just simply choose any y which is not element m, and then the last proposition will always be true, while the first one is not?
Can't you choose a... No. You see, you mean the second half of the or is always true, or what?
No, in public, in the cloud. In cloud.
Yeah, you're absolutely right. I'm very sorry. Yeah. You define it this way for the all quanter. For all y and m, and then you say for all y and m implies. And if y is not there, hang on, there's something strange. I think we want it like this. Yes, we want it like this, because if I say for all y and m the following should be true, you could certainly always choose a y that's not in m, right? And then anything I write here would always be false. We want, if the y doesn't come from m, not to affect the validity of the statement, which then only hinges on the condition being true for the y and m being true. Okay, I'm confident that for the all quanter it's correct. And then this existence quanter is defined as before. It's derived from this definition of the all quanter. Then the existence quanter, there exists a y in m such that a certain condition p of y holds, will then be defined as not for all y in m. Is it true that this does not hold? Yes. And this double knot doesn't pull into here the way I suggested. Very good observation. Thank you very much. That's very important. You define for the all quanter like this. That's exactly what we want if you think about it. And then this is related to this in the standard fashion. Thank you. Very, very good observation. So the laces of my shoes came undone because of this mistake. Okay, good. So the final axiom of the perp section is the axiom on power sets. And we all know what a power set is. The power set is the collection of all subsets of a set, right? So traditionally, no, historically I should say, historically, in naive set theory, the principle of universal comprehension was thought to be needed in order to define for any set M, this object curly P of M called the power set, and traditionally, and I remark inconsistently, well, by using the principle of universal comprehension, which is not a good principle, it's a bad principle, it's inconsistent, to say those are all the y's that are subsets of M. We collect all the subsets of M. But we cannot tell which bigger set these subsets come from if we're only given the set M. So to an extent, what you want to do in set theory, it's a very deep thing in set theory, is you want to repeatedly apply power sets. You take the power set of the power set of the power set of some other sets. We'll come back to this. And this way, you go through the entire universe of sets, if you wish. You can generate every set in set theory, roughly speaking, by repeated application of taking the power set of the power set of the power set and so on. But if you want to generate sets, it cannot be that you know before where they come from, which big set. So people thought you need this principle of universal comprehension, but we, of course, here, we lack the restriction, so we know we're not going to do it this way. Bad. And in fact, there is no other choice but to postulate that the power set exists. Instead, axiom on existence of power sets. Let M be a set, then there exists a set denoted curly P of M, whose elements are precisely the subsets of M. Example, let M be the set with the elements AB, which themselves are sets. Then the set power set of M, which is the collection of all subsets. Well, the empty set is a subset of any set. Then there come the one-element subsets of M. And then here it's already the entire set. So these are all the subsets of M. And they're all collected, if you wish, in the power set of M. And that's, of course, the standard issue power set that you know. And it's so easy to explain how to build it. You take all those things and you collect them into a set. But is the result a set? We cannot argue so by the non-existent principle of universal comprehension, because that's not a principle. We don't want that. We cannot argue so by the principle of restricted comprehension, because we wouldn't know a priori from which set the subsets come, from which bigger set, because that's just the set we want to define this way. There's no other choice but to dedicate an extra axiom to the existence of power sets. That seems not very economical. I mean, what on earth else we will come up with that we want and put down an axiom, right? Well, the power sets we want. Okay. So we have EE, perp, ICF. Let me go to the I, and then we'll continue with the rest next time. It's the axiom of infinity. The axiom of infinity is something we also want, because otherwise we don't get standard mathematics. The axiom of infinity says there exists a set that contains the empty set. Okay, that's simple enough. And with every of its elements y, well, this, of course, does not refer to the elements of the empty set, because there are none. This exists to the elements of the set whose existence is postulated, and with every of its elements y, it also contains always means contains as an element, contains the set with the element y as an element. So, remark, the smallest, the simplest, one such set is, informally speaking, the set with the elements empty set. Okay, yeah, sure, the empty set has got to be in there. But if there's the empty set in it, it should also have the set with the element empty set. All right? But if we have that, it should also have the set that contains as an element the set with the element empty set. And then it should have set, 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 empty, set, 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 and so on. Because this can serve as the y for the element y, and so on. Now, in elementary school, these are too many brackets. So in elementary school, people introduce trivial notation for this, and they simply forget the slash here, and they say this thing, we make a funny symbol like that, and for this set, these are all sets, right? For this set, we have a funny symbol that looks like that. For the next set, we write, ooh, yet another one like that, and I think you know what the next funny symbol is. So we invent trivial names for these sets. There are other sets that whose existence is guaranteed by the axiom of infinity, but this is one particular of those sets. So corollary, why not? Corollary, the set of non-negative integers is a set according to axiomatic set theory. If we didn't have the axiom of infinity, you still could, you simply could not prove that the natural numbers or the non-negative integers constitute a set. So you need this axiom to get this thing running. Now you say, well, again one of these maybe aesthetically not so appealing axioms, but you can say, okay, what's next? You require that the real numbers do always exist? Well, remark as a set, not anything further, as a set, the real numbers can be understood as the power set, or defined as the power set of the integers. And then you can again take the power set of the reals, and you get an even bigger set. And then you can take the power set of the power set of the power set of the integers, and you get a bigger set. And this way you go through the entire universe. The universe of sets, if you wish. The universe of sets. But what is this n? This n has just been built from the empty set. So up to this point, the only set whose existence we explicitly demanded was the empty set, and we already arrived at the reals. Okay? So you see, these are sometimes maybe ad hoc seeming postulates, and we haven't gotten all of them. We still need the C and the F, And the C is a special one. You could put it there, you can leave it out. It's the axiom of choice. You can have Zermelo or Fraenkel set theory with or without the axiom of choice. And the F, the axiom of foundation, says you could also have the idea that instead of building sets from the empty set, you could have a bootstrap that you say you take a set that contains itself or contains the set with the and so on and so on. And the axiom of foundation, we're going to introduce together with the axiom of choice next time, tells you no such thing can be done. And in total, it will turn out, once all the axioms are there, that essentially every set we will ever consider in standard mathematics, at least in the mathematics built on these axioms, will be ultimately, basically, constructed only from the empty set by these construction axioms we wrote down. So set theory is very simple. It's just the empty set. We continue next time. Thank you. So welcome back to the lectures. In our discussion of the 9 axioms of set theory, which were EE, perp, IC, and F, we already discussed the first 7, so that means 2 to go. And the next one is the axiom of choice. So the axiom of choice talks about a set. Let X be a set whose elements are, now there are 2 conditions, non-empty and mutually disjoint. That means if you take the intersection of any 2 elements of the set X, then this intersection will be the empty set. Are mutually disjoint, then there exists a set, let's call it Y, whose elements which contains exactly one element of each element of X. So intuitively speaking, you look at the elements of X, which are all sets, what else? And from each of these sets, you pick one element. And you collect them all into the set Y. And all the axiom of choice guarantees you that there exists such a set that contains exactly one element of each element of X. Now, an important, well, at least maybe somewhat clarifying remark is that sometimes people call this set Y a dark set. So what's so dark about it? Well, given any set X, it's not so clear. There's no clear prescription of how you pick an element of each of the elements of X, right? So that's the dark side of it. And so there's this nice, I think it's by Russell, this intuition about it. If your set X consists of sets that consist of pairs of shoes, okay? So left shoe 1, right shoe 1, comma, left shoe 2, right shoe 2, and so on. then in principle you can of course apply the axiom of choice, but you don't need to. If you look at the individual elements here, you can have an algorithm. You say always pick the left shoe. So you can build the set left shoe 1, left shoe 2, and so on. And to do this, you do not need the axiom of choice. But if instead you were to consider a set of socks, sock 1, well, sock 1 left, sock 1 right, sock 2 left, sock 2 right, and so on. I introduced this left and right only to say these are two different socks, okay? Different individual socks, but you cannot distinguish them. So you have two socks, they look the same, and in this case you need to invoke the axiom of choice. To build the set Y that contains, say, sock 1, sock 2, and so on. Because you don't really see which one you pick. You have no further means of distinguishing them. Well, it's just an intuition. It's just an analogy. Yes?
On the left-hand side, in the last sentence here, should it not mean exactly one element of each set of X? Or?
Well, the point is everything that appears is a set. So if there's an element of a set, what is an element? Well, we never talked actually about elements. It's just if you want to emphasize this lies as an element somewhere, we use the word element. But actually, elements are also sets. That's the point. Okay. So that's the axiom of choice. Further remark is that the axiom of choice is independent of the other 8 axioms. And that means we could have set theory with or without the axiom of choice. But standard mathematics uses the axiom of choice, and so will we. And one last remark is what we actually need it for. And there's a number of uses and a number of theorems that can only be proven with the axiom of choice. Two that will appear in this course are the proof that every vector space has a basis needs the axiom of choice. And also the proof that there exists a complete system of representatives of an equivalence relation also requires the axiom of choice. And today we'll talk about equivalence relations a little later. Originally, the axiom of choice was, I think, introduced by Zermelo, I'm not entirely sure, in proving a theorem that had been unproven for quite a while. And he proved it by introducing this additional assumption. So initially, there was some suspicion that this was a meaningful or a very valuable axiom, because there was a suspicion that it's only been used in order to prove that theorem. So that didn't sound so good. But actually today, we like to use this throughout. So there is nothing really about the axiom of choice that's suspicious. So the final axiom is not an existence axiom like some of the others, or a construction axiom. It's more like a non-existent existence axiom. That's the axiom of foundation. And notwithstanding its name, it was one of the axioms that were introduced last into set theory. And it says that every non-empty set X contains an element Y that has none of its elements in common, that has none of its elements in common with X. So it's a non-existence axiom, if you wish. It excludes certain situations. So it's an immediate implication that there is no set that contains itself as an element. X element X for no set X. Okay? So you may remember that when I introduced the element relation, we tried to construct the set of all sets that do not contain themselves. So there was an early attempt to exclude this. But we also showed that trying to build such a set of sets that don't contain themselves, we get something that is a non-set, because it no longer, well, satisfies the first axiom of our system of axioms. Well, that we had to give up. We also couldn't include it by a principle, a universal principle of restriction, universal principle of what was it called? Comprehension. Thank you very much. Because there is no universal principle of comprehension. There's only a restricted principle of comprehension. So after all, the axiom of foundation has to take care of that. Okay. And so ultimately, I discussed this before, the axiom of foundation also excludes that you start defining sets in this way. You could say, well, let's take a set that contains itself as an element, is self-referential, and so on. If you don't have this, then ultimately every set needs to be built of the empty set. And we saw an example of that before, where the natural numbers, the positive or the non-negative integers, were actually constructed only from the empty set. by using the axiom of infinity. So this concludes our overview of all the axioms. I repeat, it's EE perp ICF, so you should memorize these axioms. And in principle, every time you construct a set, you should ask yourself, can I actually construct the set according to the axioms of set theory we're using? And I think I mentioned this as well. This is the Zermelo-Fraenkel set theory, including the axiom of choice. So the totality of all these axioms these 9 axioms is called Zermelo-Fraenkel set theory, including the axiom of choice. Is called ZFC set theory. If the C is left out, that means you don't want to use the axiom, you don't want to assume the axiom of choice. There are other axiomatizations of set theory. They're weaker ones. I don't think they're really stronger ones. Anyway, this is again the standard set, and as far as anybody knows, all of standard mathematics is built on this and can be constructed out of this, at least in principle. Okay, so it's really worth having a close look at this, because in principle everything that follows can be constructed from there.